also like to thank the organizers for giving me this opportunity to review about six-dimensional field theory. As Neil also said, it's getting into a very big subject. And I had to think a little bit, especially considering the diversity of the fields here, what kind of subject I should talk about. I don't really work on higher structures or new formulations of quantum field theories. I'm a person who uses these old-fashioned gauge theory techniques to understand some phenomena of this six-dimensional quantum field theory. So if you don't mind, many of you can regard this as a phenomenology talk. It's good to know lots of phenomenology which could constrain the possible new structures and hopefully to guide the better and right microscopic descriptions of six-dimensional quantum field theory. So initially I tried to overview some developments of six-dimensional 2-0 theories, 1-0 theories, various descriptions, aspects, calculations, but I decided it would be better to make things simple. So I decided to focus on a few, what I think are the focal themes. And inevitably there will be some overlaps with what Neil said, but hopefully there should be something complementary. Anyway, these are all challenging subjects, so it won't be bad to repeat part of it. So I'll be trying to construct my reviews, focusing on several key themes, which I think will be putting very important constraints and guidances to the possible microscopic descriptions of six-dimensional SCFTs. And the key themes are the following. Some of them are the self-clear strings in six dimension. I'll elaborate it a bit more than hopefully what Neil said. And related to the self-clear tensors, the compactification to circle torus, we already heard about, and the S-duality also we already heard about. And try to emphasize the interrelations of these key themes. And especially try to emphasize that the challenging aspects like n to the 3 n cube or S-duality are intimately related to the physical properties of the self-clear strings. So let me start by briefly reviewing how we found it in string theory community. So in the mid-90s, there was a second string theory revolution. There was a great development in the non-perturbative aspect of string theory. And as a corollary, string theorists indirectly predicted that there should be existing a new class of interacting six-dimensional quantum field theories. The way Witten initially found it was geometrical. He put what's called the type 2B string theory on certain orbifors. Okay? So C2 modded out by an orbifold, classified by ADE. So one could give a string theory argument that there exists some degrees of freedom localized at the tip of the singularity, propagating in 6D, which further can be argued to be decoupled from gravity and all the 10-dimensional stringy degrees of freedom at low energy. So this indirectly gives a hint that a six-dimensional quantum field theory should be existing. These are called the six-dimensional 2-0 theories. And if you want to get a little bit more feeling about this quantum field theory, you resolve this singularity, and it turns out to be a bunch of intersecting two cycles. So you can wrap what's called the D3 grains on these two cycles to get some stringy objects. So these stringy objects are turning out to be charged with various two-form tensor fields. So this is very similar to what the W boson in certain broken phases of gauge theories, which are charged under the abelian one-form gauge field. So in some sense, this is a quantum field theory of charged two-form tensors, which turn out to be tensionless in the singular conformal field theory limit. As we have heard of many times, we still don't know any microscopic description, a faithful microscopic description, although one point of this conference is getting towards this. For instance, we don't know a definite Lagrangian which is proved to be described in the physics of the system, but it has been argued long ago by, I guess by Steinberg initially, that we should really abstractly view this as a local quantum field theory in space-time dimension 6. There's a much more intuitive way of viewing this. At least for certain classes of this 2-0 theory. So what is called the AN-1 type may be alternatively realized as a world volume quantum field theory on coincident M5 grains. Okay? In this case, resolving the singularity of type 2B's case turns out to be separating and parallel M5 grains in two perpendicular directions. And the strings coming from D3 grains are corresponding to the open M2 grains, suspended between these M5s. There are lots of mysteries concerning these quantum field theories. And we're starting from the fact that we lack the microscopic description, and this seems to be the quantum field theory not for particles but strings. Another interesting aspect, which is still mysterious, is that if we have a large number of n5 planes on top of each other, from various indirect gravity calculations or anomaly calculations and so on, there are signals that the larger degrees of freedom should scale like n cubed, which is much larger than the Yang-Mills theory living on D planes, which shows n squared degrees of freedom only. Okay? So these are some of the important aspects. Recently, there have been lots of generalizations to 1-0 supercomponent field theories. It's again constructing indirectly the less supersymmetric supercomponent field theory from string theory, or what is called the F theory. So basically, the transfer space it turns out to be more non-trivial 4-to-4 manifold instead of the C2, and it contains singularity, which can be again be resolved into two cycles. Okay? And there are some non-trivial fields called axial dilatons, which are the torus vibrations of these space manifolds, which make a whole Calabi-Yau space. So trying to understand the 1-0 field theories from string theory turns out that the classifications of this so-called elliptically fibered Calabi-Yau satisfy certain properties. So there are lots of interesting works on this. And there's now an understanding that there's an abundance of 6-dimensional supercomponent field theories that can be predicted from string theory. From pure quantum field theory points of view, all these models are equally mysterious as the 2-0 theories. And the universal aspect is that in all these kind of 6-dimensional component field theories, they turn out to be stringy objects, coming again from D3 branes, wrapping slightly resolved 2 cycles, and the remaining direction becomes the strings. And these are again charged under the 6-dimensional tensor field. So this is one of the universal aspects of 6-dimensional field theory. So I repeat this aspect in a little bit more detail. In all supercomponent field theories, 2-0 or 1-0, there turns out to be a universal object like strings, tensors, and associated with that, there turns out to be a universal branch, which we call the tensor branch. A branch or the phase of quantum field theory is obtained by giving some expectation value of the scalar operator. And the scalar operator in consideration is a real scalar operator, which is sitting in what is called the self-dual tensor multiplex. So it consists of a real scalar and a two-form tensor whose field strength are constrained to be self-dual and some fermions. So the 6-dimensional CFTs can have many numbers of tensor multiplexes. But if you go to tensor branch, you only have to specify the number of abelian tensor multiplexes. And if you give generic values to all these scalars, you go into the tensor branch. It's like a Coulomb branch of 4-dimensional gauge theory. So giving that expectation value of the scalar and going to certain branches breaking conformal symmetry corresponds in geometry of 2B or F theory. It corresponds to resolving the singularity into some intersecting 2 cycles. And in M-theory setting, with M5 planes, going to tensor branch corresponds to separating the parallel M5 planes. So all we know about, we don't know about microscopic formulation of the 6-dimensional theory at the conformal point, but in the tensor branch, we know some effective actions, okay, which contain a bunch of abelian tensor multiplier fields and optionally other fields. So this is an effective field theory, which is valid as long as the energy of your interest is much smaller than some powers of this scalar there. So the 6-dimensional multiplexes in the tensor branch can consist of some numbers of abelian tensor multiplexes, some vector multiplexes, which can be non-abelian, and optionally some hypermultiplexes. And yeah. So there have been some approaches from conventional quantum field theories, mostly conventional gauge theories based on Lie algebra, but these are not completely satisfactory microscopic descriptions. Various conventional quantum field theories are serving as either effective quantum field theory in certain limits, like tensor branch, or some exact descriptions of 6-dimensional quantity in certain large degrees of freedom limit, like the deconstruction limit that Neil has explained to us in the previous talk. So the usage of these quantum field theories are sort of subtle to understand some 6-dimensional physics. well, some of them play very subtle roles, such as the 5-dimensional Yang-Mills, which I'll try to explain more later. So I try to discuss some insights that we can, limited insights that we can obtain from various quantum field theory descriptions in the conventional sense, to understand various phenomenological constraints, which hopefully will serve as constraints or guidances to true QFT to be found in the future. The key concepts I try to explore today are, as I advertised, 4-dimensional S-duality after compactification, and its generalization to higher dimensions if you compactify the systems on a finite torus, and various 6, 5, or 4D descriptions of these phenomena. And also talk about the n-cubed degrees of freedom which can be captured by certain Cartesian function counting states. And finally, I try to emphasize the role of self-zero strings. And especially I try to emphasize that the physics of self-zero strings are intimately connected to the property of S-duality or n-cubed degrees of freedom. Well, in a sense, self-zero strings are non-abelian degrees of freedom, analogous to W boson. So intuitively, it sounds heuristic that there may be some hints on the non-abelian n-cubed degrees of freedom in it. But trying to make that expectation quantitative is very challenging. And I'll try to give you a hint, at least in some specific setting, that the physics of self-zero strings are indeed encoding n-cubed in a very subtle but elegant manner. Also, I try to explain the role of these self-zero strings in S-duality within this conventional field theory approach, which are very limited actually. So let me first try to explain to you in a bit more detail the tensor branch and the physics and the brief and the qualitative physics of self-zero strings that you encounter in the tensor branch. So, for instance, let me just consider the simplest case of superconformal field theory, which only has one-dimensional tensor branch. So if you go into the tensor branch, you only have one abelian tensor multiplet. Okay. So the 2-0 theory corresponding to this case is what's called the A1 superconformal field theory. It's describing the two parallel M5 and the relative motions of them are the scalars in the single abelian tensor multiplet. Okay. So you have one 0 tensor multiplet, and you address it with a neutral hypermultiplet, and the tensor branch effective field theories are just the free field theories consisting of these n equal 2 tensor multiplets. More elaborate structure of effective action is given by n equal 1, 0 theories, because in this case they can be tensor multiplets, and depending on models they can be non-abelian vector multiplets and hypermultiplets. And the real subtlety in this action is the subtle interaction having to do with the tensor and non-abelian vector multiplets. The bosonic part of the action takes the following form. It has the quadratic kinetic term for the tensor multiplet field. Of course, in the sense that, of course, it's subtle to write down the self-zero tensor multiplet action. So, if I say the action is first ignoring the self-duality condition, you write the equation of motion and impose the constraint by hand. So it's like you just type to be supergraph the action. And its coupling to this vector multiplet fields, which can exist, are very subtle, and it's dictated by what's called the 6-dimensional Green-Schwarz anomaly cancellation mechanism that we heard of yesterday. So you have to write down a characteristic gauge non-invariant interaction terms, which will cancel the one-loop part of the anomalies in the tensor branch. So it gives you the characteristic coupling between tensor multiplet fields and the vector multiplet fields. So for instance, the scale invariance of the 6-dimensional theory is formally respected, all fields at dimension 6, and it's only spontaneously broken by the expectation value of the scalar. So these are the tensor branch effective and the structure of the tensor branch effective theories. And the important object I'd like to keep emphasizing is the self-zero strings. Okay. Since I have a self-zero tensor field, there can naturally be tangential objects in the tensor branch which are charged under it. But naturally, and in the string theory, these come from open N2 grains or wrapped V3 grains. But due to the fact that these fields are self-dual, the field strengths are obeying self-dual conditions, these self-zero strings are having equal electric and magnetic charges under this B mu tensor field. Thus we call it a self-zero string. So for instance, in the 2-0 theory, in the effective theory, the tensor branch, you only have the tensor field. The relevant equation of motion with this self-theory string source is that the equation of motion equal or identically Gauss law, identically the Bianchi identity, having the following delta function-like source in the transverse 4 dimensions. And the BPS equation for either BPS or anti-BPS self-theory strings are obeying these kinds of equations. In general 1-0 theory, the structures are much more involved. The generalization of this equation, the equation of motion, identically the Bianchi identity, acquiring the source from this f wedge f of the vector multiplier fields. This is the instanton number density. So if there's a string, there's a transfer space R4, and the self-theory instanton solitons, or anti-self-theory instanton solitons, are serving the smooth source of the self-theory strings. Okay? So this gets realized in many 1-0 theories as smooth solitons, rather than having this point-like delta function sources. And as I said, these strings are analogous to W bosons of Yang-Mills theory in many ways. And we can regard these W bosons as trace of non-abelian degrees of freedom in the broken phase. So you have n by n matrices, you go to a phase in which non-abelian gauge symmetries is broken to cartons, and W bosons are just the off-diagonal complements. Okay? So with this crude analogy, we can expect that the self-theory strings could encode some kind of non-abelian information about the 2-0 theories. Okay? Although we don't know how to precisely formulate it, with limited techniques, we can try to precisely compute some concrete numbers and get some hints out of it. So that's a phenomenology I'd like to develop, one of the phenomenologies we say. Yes,
so what is F there?
This F?
Yeah, you don't have a gauge field in the...
Oh, this is the field strength of the 6-dimensional vector multiplier, which may optionally exist in 1-0 theories.
Okay.
In 1-0 theories, we have abelian tensor, optionally non-abelian vectors, and non-abelian hypers, but hypers don't participate in this equation.
But there is no guarantee that you can do that for all the self-theory strings, right?
There's
It
no
depends very much of whether you have...
All the self-theory strings means all 1-0 theories?
So if you have a given 1-0 theory, you cannot probably not express all the self-theory string as instanton in this way, because it depends very much on the group.
Well, of course, you can consider some singular sources, but that can be realized as a singular limit of this instanton. Instantons have moduli, so they can be, if you make this smooth instanton point-like, it naturally includes the singular configurations. So this is I would say, the most general representation of the self-theory strings in the effective field theory.
But for example, what if you have a SCFT that has tensor multiplets but no vector multiplets?
Oh, in that case, yeah, some 1-0 theory have joint testers without Yang-Mills, and in this case it behaves like the 2-0 self-theory strings. It behaves like a delta function external source, yes. Only if you have non-trivial vector multiplets associated with every tensor multiplet, then you can do it this way, yes.
And this self-theory only lives in 60?
Only lives in 60.
In 60.
You mean not in which thing?
Well, so
Not in 10?
10.
Oh, yeah. These are solitary objects which are stuck to the 6-dimensional CFTs.
So I think of the 60 as being a magnification of type 2B.
Oh, yeah.
This
You asked me whether something can escape or not.
Yeah.
Oh, yeah. Answer is no. The thing is that the strings are rising as this 3 branes wrapping these 2 cycles, and it can't really escape. It's energetically prohibitive. Yes. Other questions? Yeah, so with the hope that they may encode some non-abelian degrees of freedom, let's go and see. I present the salient physics of self-theory strings here. I'll talk more about it later, connected with other important themes. Now let us explain the relation between the self-theory strings and the electromagnetic or S-duality that we also heard from Neil a lot. So we consider the 2-0 theory compactified on a torus with suitable complex structure. In the small torus reduction, we know there is a maximal superharmonic body, where the complex structure is realized as complexified gauge coupling and the theta angle. And the electromagnetic duality is basically saying that if we invert the coupling constant and change the role of magnetic monopoles and electric particles, the theory remains equivalent to the previous one. Okay? And the 6D origin of it is very obvious because, you know, in 6D you have strings which have equal electric and magnetic strengths, so you intrinsically have just one object. So W boson and monopole, say the Coulomb branch, emerge depending on which circle of the torus you wrap these self-zero strings on. So the distinction between electric and magnetic particles just becomes geometrical in this 6-dimensional viewpoint. So it naturally explains S-duality, which is a very non-trivial and non-perturbative property from the viewpoint of 4-dimensional gauge theory. More generally, we expect SL2Z duality, where it is SL2Z geometrically latched on the torus. And this aspect, is both a benefit and a challenge depending on your viewpoint. If you want to understand some aspects of 4-dimensional gauge theory's dualities from a more geometric and simple point of view, the mere existence of these 2-0 theories helps a lot. Okay? So it has been used extensively in the recent literature to compactify the 62-0 not just on torus but on a more complicated Riemann surface. And many of the non-trivial duality properties of 4-dimensional gauge theories get geometrized, and you can get a more coherent understanding of them. Or more complicated dualities could even be discovered using this geometric viewpoint, compactifying the 2-0 theory on Riemann surface, or even in some higher dimensional 3-manifold or 4-manifold, to get the intuitions on the strong coupling dynamics of lower dimensional quantum field theory. However, from the viewpoint of formulating microscopically the 6-dimensional quantum field theory, the task that we have to explain S-duality naturally would be a big challenge, because we definitely have been knowing that it's been a very tough problem, a tough fact to establish from standard gauge theory. And the microscopic formulation, hopefully if it's a covariant formulation in 6D spacetime, should probably be realized so naturally and manifestly. I believe similar issues concerning the self-zero strings and 4-dimensional gauge theory surely exist in less supersymmetric cases, but to focus on simple aspects, let me focus in most cases on the 2-0 theories and compactifications on torus. So, I talk about two compactifications, and let me phrase it as okay. So it's illustrating to make this torus compactification stepwise. So let me first compactify the system on a circle, and then on the second circle later. Okay. If you compactify the system on a single circle with radius r, as Neil already explained to us, one obtains maximally supersymmetric Yang-Mills theory in 5 dimensions, when the energy scale is much smaller than 1 of r. So 5-dimensional maximally supersymmetric Yang-Mills theory consists of vector multipliers and 5 scalars. And these 5 scalars are roughly speaking probing the transverse space directions of NG4 branes that we obtain by compactifying n and 5 branes on a circle. As Neil explained to us, the dimensional parameter G Yang-Mills theory of 5-dimensional Yang-Mills is identified with the radius of the 6th circle. And it provides a weakly coupled description when the energy scale of an interest is much smaller than this energy scale. Namely when the 6-dimensional color plane was heavy. And as Neil mentioned, these naive reductions of, let's say, Lagrangian quantum field theory description on a small circle gives you a coupling which is inversely proportional to the circle radius. So it becomes strongly coupled in infrared. But the phenomenon that we observe here is that the opposite. Okay? Morally, I understand it as the following. Since the 6-dimensional field theory that we are after should be a sort of tensor theory, and the final theory we obtained is a kind of vector theory, I always very hazily understand it as that to obtain this low energy description, some kind of tensor vector duality should be involved, although I have no idea what it means in non-abelian sense. And that should be possibly giving us this a little bit odd phenomena that if you go to small circle limit, you get weakly coupled description. But anyway, this is the characteristic feature. And this gauge theory description turns out to provide great intuition on this system in the past few years. Neil already talked to us, but it's, in the modern version, it's basically him and his collaborators and Mike Douglas, who suggested it. And I'll talk a little bit about that from my viewpoint as well. I think the key excitement, interesting feature of this 5-dimensional Yang-Mills theory is that if you look into this soliton sector, it sees the apparently lost Kaluza-Klein degrees of freedom of the 6-dimensional field theory. The rough way of that, the way that's made possible is already explained by Neil, but it's basically what's called the instanton solitons. It's mathematically the same instanton, satisfying the same equation, but it plays different role than the instanton that I explained in the tensor branch effective action. These are, in the 6-dimensional tensor branch, these provided the source for the self-field strings. Here in 5-dimensional Yang-Mills, it's mathematically the same object, but it's a confusing terminology. It's a particle-like soliton. And these are realizations of D0 branes bound to D4. And so if you invoke the string theory and M-theory dictionary, these turns out to provide the non-zero Kaluza-Klein particles of the M-theory compactified and so forth. So if you study the sector with non-zero D0 brane solitons in 5-dimensional Yang-Mills theory, you are able to provide the 6-dimensional physics with definite non-zero momentum along this circle. So this made the study of 5-dimensional Yang-Mills very interesting. Okay, so after this 2010 paper, I decided to study some aspects of this solitonic sector of this 5-dimensional maximum Yang-Mills. One of course have to worry that, that this is a non-normalizable theory with coupling constant being the positive dimension of length. So one really has to worry whether it's possible to make consistent quantum calculations or not. But I'm a concrete person, so I decided to shut up and do calculations with simple observables and see what I get. Okay? So if there's some pathology, it will show up during my calculation. So it's a system with supersymmetry, so there are subclass of observables which you can really easily compute and exactly compute, even at a strongly even at generic coupling constant. These are called, these are some supersymmetric partition functions as an example. More generally, these are observables which are represented by path integrals respecting certain supercharges. And using the power of this supersymmetry, you can often carry out exact calculations. And due to the help of this supersymmetry, normally the observable tends to suffer much less from the wild quantum fluctuation than generic observables. So I thought that was the safest point to start the studies. So I decided to study certain supersymmetric partition functions, which I'll explain in detail in the next slide. But at least apparently, I'm not sure about the status, final statement I should mention here, but at the apparent level, if you do the quantum calculus of Yang-Mills instantons carefully, you see a little bit of UV incompleteness, which I think might be inheriting from the UV incoupling of 5 Yang-Mills theory. But as I explained to you, the nature has to be clarified more. But anyway, if you choose a careful observable, this UV incompleteness is not as violent as what you naively expect as UV divergence or so on. For instance, if you compute some SUSY supersymmetric observables, you're forced very often to consider the moduli space dynamics of these solitons, which are instantons. And these instantons are infamous for having the singularity of the moduli space, which are called small instanton singularities, creating possible ambiguities of the calculus. For instance, you are led to do some path integrals of nonlinear sigma model quantum mechanics, which has some singularities on the target space. It's always a conical singularity. This is a modular space metric of single S-units. I think you always find conical singularities. So, well, this is a generic phenomenon that you encounter both for maximal super-Yang-Mills theories or n equal 1, so less supersymmetric Yang-Mills theories. So, practically what we did was, whenever we encounter such kind of small, very mild UV incompleteness, we could easily cure this by a simple UV completion within the instanton quantum mechanics, the soliton quantum mechanics sector. We don't know how to UV complete or, wide quantum field theories, but if you think we encounter small UV incompletion in quantum mechanics, we could easily cure it, say by using the help of string theory, uplifting this quantum mechanics by, let's say, a D0, D4 system by, given by string theory. So this way you can provide certain UV completion and give some faithful calculation about the instanton observables. Mostly based on 5-dimensional Yang-Mills theory, but one might view that there's a little bit of extra illusion that put in. this story is actually going much more general than maximal super-Yang-Mills. Although 5-dimensional Yang-Mills theory providing certain descriptions of 5-dimensional CFTs with less supersymmetry, and the framework I explained to you just goes through for all examples. But maximal super-Yang-Mills has more symmetry, so there might be some exceptional structures, which I didn't really carefully clarify yet. Perhaps with the help of maximal supersymmetry, one might be able to show that even at the level of nonlinear sigma model, there should be a unique way of dealing with singularity, and you don't really have to invoke the usual completion within there. There are some hazy stories which I really didn't clarify. So, but anyway, I'm a practical man. Once I could compute, I decided to forget about it. So I never resolved this problem myself yet. But I think it's a good testing ground of some thoughts presented in this paper, that maximal super-Yang-Mills theory in 5 dimensions could be a quantum definition of 6-dimensional 2-0 theory. I don't know how to test it in full generality, but in this small mini version of supersymmetric observable, you observe very minor possible UV ambiguities. And whether it can be resolved within 5-dimensional Yang-Mills theory or not, it's a mini version of the test. So I think still there's a good way of testing this proposal in a smaller version. But anyway, we could compute some observables, optionally with some small UV completion. And we did the calculation for what I call the D0, D4 system. So it's just the D4 brane, the stack of D0 branes bound to that. And the number of D0 branes are setting in the Kaluza-Klein momentum sector. So it's really a 6-dimensional space. So it turns out just to be the Witten index. It's a quantum mechanics. So the supersymmetric observable you can count is a trace of the Hilbert space of K instanton. But to use the help of supersymmetry, you have to carefully design the observable in a way that you count the number of bosonic states, and you insert a -1 to the fermion number, so you subtract the number of fermion states. So we call this a Witten index. And we can, to maximize the information, and for certain reasons that I won't emphasize here, you can dress all this counting of bosons and fermion states with lots of chemical potential factor. Epsilon 1 and epsilon 2 are called omega background. This has been pioneered by Nekrasov and before that Hollowwood or I think. But they are the chemical potential for the spatial rotation R4 mixed with some R symmetries. And you have some chemical potential for the electric charge, which corresponds to scalar expectation value. And for the rest of the R symmetries, we introduce some mass parameters, chemical potential.
So supersymmetry is broken to n equals to 1, right? Because of the locations?
Chemical potentials. Yeah, it's broken to 2 Hermitian supercharge, Q and Q dagger, which you need to secure to define the Witten index. So I introduced maximum number of chemical potentials because they give more information. And this kind of Witten index and more generally supersymmetric partition functions of quantum field theories have been there has been big advances in recent years to compute these quantities exactly. Actually, this quantity is calculated actually very, very long ago for massive form maximal super-Yang-Mills theory by Nekrasov in 2002. So that's much, much long ago. And the result is looking complicated, but you don't really have to know the detailed form. It turns out that the K instanton partition functions are given by certain resid sums as a result of quantum integral, and each resid and poles are classified by certain Young diagrams. So functions of chemical potential. You just suffice to remember that there's a concrete expression given by some quantum mechanics calculation. And if you form a grand partition function of that, summing over these non-perturbative particle numbers with its own figures to introduce, it turns out to be abstractly a partition function of 6-dimensional theory R4 times T2. Where the first circle of T2 comes from the circle compactification of the spatial direction. Second circle can be regarded as a Euclidean temporal circle, because I introduced lots of chemical potentials. One of them can be regarded as an inverse temperature-like variable. So it's spontaneously compactified in a thermal-like quantity. So it's abstractly a Euclidean partition function of R4 times T2. You can regard that. So the question is, this quantity contains lots of important, hopefully important spectral data of 6-dimensional superconformal field theory with all Kaluza-Klein momentum mode capped, even though in the BPS sector only. So that kind of things has been studied over the past few years. For instance, it's very easy to see that the single M5 brane theory is really reproduced by studying the partition function where there's just one D4 brane. Okay? You can use various identities to show that the grand partition function is taking the form of a simple plasticity exponential, and this is precisely equal to the partition function of single self-theoretic tensor multiplier field on circle compactification. But to understand the full non-abelian implication of this quantity, it's a horribly complicated quantity, even though explicit, and especially we don't know how to exactly sum up all these series having to do with these particle numbers. So especially at large circle radius, when you decompactify the CC regime, where most interesting things is expected to happen, you'll have to wait for a few minutes, some minutes, or a few slides later. Because I have to develop a little bit more sophisticated techniques on self-theoretic strings to extract out the really interesting non-abelian physics out of this quantity. But the thing what we expect is very, very challenging. You know, in six-dimensional conformal field theories, you don't just expect to find n cubed. So, but if you compactify the 6D theory in a circle, it should be having a strange interpolation of degrees of freedom. As Neil emphasized to us, for small circle radius, we only expect n squared degrees of freedom because we know that there should be a weakly coupled Yang-Mills description with n squared degrees of freedom. Only if you enlarge the circle radius compared to other chemical potential scale or temperature scale, you'll find that the degrees of freedom are enhancing to n cubed, depending on whether this instanton solitons are heavy or light. So this is a very non-trivial phenomenon that any microscopic formulation should realize. Anyway, this is a kind of non-trivial calculation which can be done in 5-dimensional setting. You can further compactify down to 4 dimension on a torus, and I'll explain to you the salient aspects of S-duality. Mainly, just to repeat it once more, the electromagnetic duality basically says the 6-dimensional CFT says that the electric magnetic particles or electric magnetic fields in 6 dimension basically has the same origin, and this leads to what is called this naturally explains what is called the Monton and Olive S-duality, electromagnetic duality. And Monton and Olive in earlier days has observed that only with n equal 4 theories where this S-duality can be naturally realized because these electric and magnetically charged particles have the same type of supermultiplier contents. Okay, so that was a kinematic observation. To actually show dynamically that the S-duality exists, one needs to do a lot of harder work. For instance, in early 90s, Seok has done a really powerful work of studying the electromagnetic diode spectrum in the Coulomb branch and show that the spectrum respects the SL2Z duality, which was regarded as the first non-trivial evidence, if I remember correctly, without controversy, of this duality. And many other observers have been studied in Coulomb branches and in the unbroken phase, starting from certain curved space partition function and so on, which further justifies the SL2Z duality more extensively. But these hard works are done to establish the evidences of S-duality of 4-dimensional gauge theory. But we should really remember that in terms of current gauge theory, electromagnetic duality is not manifest, it's just an emergent property. Okay? For instance, if you go back to what Ashok Sen did in the diode counting, to get the W boson spectrum at zero magnetic charge is just obvious. We just read off the spectrum from elementary fields, but to compute the spectrum of non-trivial diodes, you really have to do hard work. You have to go to the magnetic monopole moduli space, you give some electric charge, and compute the wave functions of bound states elaborately. And after that emerged that the spectrum respects electromagnetic duality. Okay? And I'm just repeating myself and following what means that. But this might be the bad aspect of gauge theory. It's not really friendly to electromagnetic duality. It intrinsically treats electric and magnetic fields in a biased way. Unlike what we expect from covariant formulation of 6-dimensional 2-0 theory. Okay. So far I explained a few apparently remotely related things. I try to explain to you the universality of tensor branch and the existence of self-dual strings in all 6-dimensional CFTs. And focusing on the examples of 2-0 theory, I explained to you some calculus of spectrum using exact calculation methods using the 5-dimensional Yang-Mills approach. But the details of this physics contained in this partition function is left on the press. Let's say whether it has n cube scaling, degrees of freedom, or so on, because we need some more techniques. And I explained some aspects of S-duality and the challenges and constraints that it puts on microscopic formulation. Now I turn to explain in some remaining time. Explain that the second and third aspect, which I regard that as some of the main challenging aspects of 2-0 theory, can be addressed slightly better by studying the self-dual string physics. And the self-dual strings having various aspects, but if you're very interested in conformal field theory, they are strictly tensionless objects. Okay? If you put M5 rays on top of each other, the open M2 suspended between them becomes tensionless. I don't know how to describe that. There are some descriptions on tensionless limit of fundamental strings. I'm not even sure whether it's applicable to this setting. So I shall explain aspects of tensionful strings existing in the tensor branch. Okay? And even in this limited setting, I'll be able to show you that many aspects of these strings are different from fundamental strings, and these aspects can be used to better understand challenging aspects of 62-0 theories. And the approach, and there are many approaches that have been developed to better understand the physics of these strings. One approach is to find out and use a two-dimensional quantum field theory description living on the worldsheet of these tensionful strings. There are other more abstract approaches like modular bootstrap and using topological string approach. It's an exciting intersection between quantum field theory and string theory and more abstract methods of field theory. But if we have some two-dimensional quantum field theory description living on these strings, the general expectation we have is the following. So I'll be presenting to you a class of two-dimensional gauge theory descriptions, which are not two-dimensional conformal field theory that we expect to live on this self-dual string. But this quantum field theory has two-dimensional dimensional coupling, so we expect that it to be weakly coupled in UV, and it will be flowing to strongly coupled fixed points living on these strings. So after RG flow at the strong coupling point, at the infrared, the fields of the self-dual strings is expected to emerge. This kind of study is somewhat like studying the massive particles of like 4-dimensional dions in the 4-dimensional gauge theory in the Coulomb branch. So for instance, to study some spectrum of n equal to dions in 4-dimensional gauge theory and the wall crossings and so on, many people have invented and studied what is called the quiver quantum mechanical gauge theory, which is supposed to be describing the physics of these electromagnetic particles. So it's kind of analogous study that I'm going to make in 60. Use two-dimensional quantum field theory, quiver quantum field theory approach to study the 6-dimensional soliton. And it's really analogous to the 4-dimensional problem that the 4-dimensional gauge theory may or may not have Lagrangian descriptions. Many of them have Lagrangians, but by now we know lots of non-Lagrangian 4-dimensional gauge theories, which is called Archer-Douglas theories, Mina and Mashansky theories. We know lots of examples similar to 62-0 theories. But even for these theories, they have Coulomb branches, and if you go into them, even though we don't know the full 4-dimensional non-Lagrangian field theories description, we know some quantum mechanical microscopic description for the massive diodes. Okay? So we restrict our interest to certain subsector, and we use some two-dimensional quantum field theory description to describe this kind of string object in 6 dimensions. And as I'll try to briefly show you, I won't be too technical, but just to briefly warn you, this kind of business involves a kind of art. You cook up a UV quantum field theory, and you expect it to RG flow to certain superconformal field theory of interest. And it's not always true that there's a unique UV quantum field theory. You can cook up multiple UV quantum field theories that flow to the same infrared point. And depending on which UV theory you pick it, the calculation may be easier or difficult and so on. It's like this 6-dimensional maximal Yang-Mills theory and ABGN that Neil explained to us. ABGN is conformal, but of course it's exactly conformal, but three-dimensional Yang-Mills theories are UV free theory. It flows to ABGM theory, but it's very difficult object to use to compute some strong coupling quantities. So depending on which UV description you choose, your life may be easier or may be difficult. So let me explain to you the main example of the self-zero strings in multiple M5 plane theory, the 2-0 theory. I told you that I'm going into the tensor branch, so I separate the N M5 planes. And to easily obtain the gauge theory, I make a UV deformation, some kind of deformation of this into the type 2A string theory setting. So in type 2A string theory setting, M5 plane can be replaced by what's called the Weierstrass spine plane. So there are N Weierstrass spine planes separated. This is the tensor branch. And the open M2 branes suspended between these 5 planes are replaced by V3 branes. If you just consider this kind of setting, a 2D gauge theory living on this self-zero strings can be easily constructed. It's basically a version of quiver gauge theory worked out by Hanani and Witten long ago in different dimensions. But it turns out that this is very difficult quantum field theory if you want to do any calculations, because this is a UV quantum field theory. If you want to probe the infrared strong coupling dynamics, sometimes you can't do calculations easily using the UV description. And more recently, a bit more clever description has been created by Hagidat and collaborators, whose idea is basically putting on just one D6 plane. And if you use some string theory argument, you can really show that if you float to infrared, the effect of the single D6 plane in the infrared dynamics is really wiped out. Just because of the fact that D6 uplift to a single tau node, and in the strong coupling limit, it just becomes flat space. But it's a slightly different UV embedding of the same self-zero string quantum field theory, and the resulting quiver is the following. Depending on how many strings you suspend between adjacent M5 planes, you have quivers, UK type quivers, where Ks are denoting the number of self-zero strings in each segment. And you have lots of fermions and bosons and supermultiplex of fields, bifundamental quivers. So this is a quiver type of quantum field theory that is supposed to describe self-zero strings, multiple self-zero strings in the infrared. So if you carefully use this theory, you can compute some quantities of self-zero strings. Similar construction can be done for the 1-0 theories, and many interesting things can be done. But I think I don't have to emphasize this too much. Actually, there are many interesting works being done in 1-0 superconformal field theory strings connected to the dynamics of instanton string worldsheet dynamics. There are lots of interesting works trying to compute exact quantities starting from these quiver type gauge theories, or from modular bootstrap, topological strings, or combining all these approaches. There are many exciting works going on, and probably there will be something nice here as well. But I focus on 2-0 physics for now. So I gave you some UV quantum field theory description in 2 dimensions, and you can really rely on string theory argument if you believe in string theory, that at the infrared, you should be flowing to a strongly coupled superconformal field theory, living on the wall volume of these self-zero strings. Okay? But that itself does not guarantee that you can compute any observables of self-zero string physics, because if you're at a strongly coupled point, it's very hard to do any computation even in 2-dimensional field theory. So in this situation, something easy to compute, select a careful set of observables which are invariant on the RG flow. Some observables that are enjoying supersymmetric non-renormalizations and so on. And a typical example of that are the supersymmetric partition functions, observables which are given by path integrals which respect certain supersymmetries. And then you can use the technical supersymmetric localization to do an exact calculus. You can do the calculation in UV, but you can trust that it is valid all the way to IR. So the elliptic genus is, from a field theory point of view, is nothing but the torus partition function of the Euclidean quantum field theory, preserving certain supersymmetry. The Hamiltonian viewpoint of that is that you compactify the spatial circle and consider the spectrum of BPS states carrying various flavor symmetries and carrying also non-zero momentum. Okay? So since you also introduce chemical potential, you also compactify the temporal direction, so it gets realized as torus partition functions. As in Witten index, it counts bosonic states, minus fermionic states, and you label it with lots of chemical potentials. I won't even bother to remember what they are. But there are many chemical potentials, and this elliptic genus, torus partition function, can be computed by using lots of advances in the recent supersymmetric quantum field theory techniques, or alternatively using some topological string calculus. Okay? So for given number of self-pure strings, there are n-1 numbers of these integers n. They turn out to be the winding numbers of strings in each segment. Okay? So this n1, n2, n3, all the way up to n sub large n-1. So these are string winding numbers. And using some quantum field theory techniques, use of free quantum field theory techniques, so the partition function, the elliptic genus, turns out to be some sums of ratios of Jacobi theta functions. Arguments looks very complicated, but it's a straightforward expression. And again, in form of grand partition function, summing over all the string numbers with its fugacity, the scalar pair, and dressing it by the n abelian tensor multiplex contribution, and also by some 0-point energy factor, you get a grand partition function, which you can again regard it as a partition function on alpha times T2. Where this time T2 is just world volume, world sheet of this self-pure string. So you should regard this as alpha times T2 partition function as the same partition function computed from 5 Yang-Mills approach coming from instanton partition functions, where this modular structure is much more transparent in this self-pure string point of view. So, as I told you, okay, so I'm going to use this self-pure strings partition function, or the grand partition function, to study some aspects of S-duality, or perhaps use S-duality to understand the challenging aspects of M5 brane theory, like Tensor cube. But let me first explain to you that this partition function of self-pure strings are behaving very different from the partition functions of, let's say, elementary fundamental strings, which are often given the realization of nonlinear sigma model on target spaces, and depending on the string numbers, the target space becomes a symmetric product of the space-time. Okay. And the fundamental strings partition functions, if you consider the multiple strings partition function, they are related to the single string partition function by the simple transformation called the Hackett transformation formula. And the structure goes as follows. For the fundamental strings, if you know the single fundamental strings partition function, 1, where the modular parameter is tau, the complex structure of torus is tau, and Z collectively denotes other chemical potential. Multiple strings partition function is given by the simple transformation formula given as follows. This is called the Hackett transformation. And this is a simple consequence of the multiparticle nature statistics of the strings and inclusion of twisted sectors. But you can show that the self-pure strings elliptic genus that I just presented to you doesn't obey this formula. And it really implies, the interpretation of this is that there are more non-trivial bound states of self-pure strings than you observed in the fundamental string sector. So it's, in this sense, it's an intrinsically different object. An easier way to understand the violation of this Hackett transformation formula, characteristic of fundamental strings, is to study a little bit of this S-dual modular transformation property. So this is a torus partition function. You can apply various SL2Z transformation of a torus, changing this modular parameter according to the SL2Z matrix, and see how the partition function transforms. This is a little bit certain partition function, so it turns out to fail to be modular invariant. Some salient reason is that this CFT is a non-compact CFT, so it has non-compact moduli spaces. So to make it well defined, you introduce lots of chemical potentials or massive parameters for infrared regularization. After you do this, it fails to be exactly modular, but has some kind of modular anomaly. So observing the pattern of modular anomaly turns out to be extremely interesting and important to extract out important physics of the 16 CFTs. So if you just apply the S-dual transformation rule of the theta functions in the previous formula, the following S-dualized partition function turns out to be coming back to its original one with a simple modular anomaly factor, depending on the string numbers. And the fact that, this is a consequence of very, very simple computation, but it has a term linear in the string number and quadratic in the string number. But if you stare at the expressions of this Hackett transformation never allows you to have this quadratic anomaly. It always requires a modular anomaly to additive. if you add the string numbers. So mere fact that the quadratic part is a modular anomaly simply proves that this formula cannot be true. And if you stare at this modular anomaly a little bit, you can extract out lots of interesting information concerning S-duality and six-dimensional entry. It's obviously related to S-duality or four-dimensional Yang-Mills theory because this is the complex structure parameter of the torus on R4 times T2. So if you abstractly regard it as a torus compactified setting, it should be, in case you take the torus size to be small, it should really reduce down to S-dual transformation of maximum super Yang-Mills, especially in this grand partition function setting. So it's natural that the S-dual modular anomaly of the elliptic genus has something to say about the S-dual transformation of the self-dual strings. And more furthermore, it's a full six-dimensional uplift when you compactify the system on finite torus. But to address this kind of aspect, let me try to introduce to you, or remind you, if you already know, some related materials about this kind of partition function, which we collectively call Nekrasov partition function. So this kind of supersymmetric partition functions are defined in either the Coulomb branch or Tensor branch of the gauge theory. The symmetries are broken to the abelian parts. And Nekrasov originally designed this kind of observable in 4 or 5-dimensional gauge theory, but it applies to 6-dimensional theory as well. He originally devised this kind of partition function to systematically understand the Seibel-Witten theory of 4-dimensional n equals 2 gauge theory and its higher dimensional version. So the relation between this partition function and the Seibel-Witten theory, it goes as follows. The Seibel-Witten theory is characterized by the single holomorphic function, narrowmorphic function, called the prepotential. If you take the free energy, log z, and take the angular momentum deformation parameter to be 0, it corresponds to a certain large volume limit, the free energy diverges, and this coefficient turns out to be what's called the quantum prepotential, which means the one loop plus non-perturbative correction of the prepotential function. If you add the classical part, it becomes a prepotential. So the Seibel-Witten theory gives us a way of computing or formulating this quantity using this A and B period integrals. And Nekrasov partition function provides an alternative way of microscopically computing the coefficients of the series expansion coming here. And in this setting, the S-dual modular anomaly of the elliptic genus I explained to you should be determining the S-duality property of the n equal 4 super Yang-Mills in the small torus limit, and it should provide a finite torus generalization of that. In the 4D limit, we already know what kind of S-dual transformation prepotential should undergo, because in the Seibel-Witten theory, the electromagnetic dualization goes by the Legendre transformation of the prepotential. So the prepotential in the electric frame gets dualized into prepotential in the magnetic frame by doing this Legendre transformation. And electromagnetic duality in Coulomb branch basically demands that the transformed free energy, the prepotential takes the same functional form if expressed in terms of the dual coupling and the dual Coulomb branch. So if this kind of phenomenon exists, the dual prepotential, the functional form of the prepotential or free energy at strong coupling is very intimately related to the free energy at the weak coupling. Okay. If you consider the full 6-dimensional extension of that in R4 times T2, if you know the 6-dimensional physics, you can't really expect that S-duality can be as simple as this because of the following reason. So S-duality relates the strong coupling region and weak coupling region. And recall, I didn't explain to you, but Neil explained to us that this tau, complex, the complex structural coupling is the radius, the ratio of the two radii of the two circles consisting, making the torus. So if you consider the weakly coupled limit, it corresponds to the small spatial circle radius compared to the temperature scale. If you go to the strong coupling region, it corresponds to a decompactifying 6-dimensional region. And we know that its degrees of freedom should be different. In the small circle region, relying on the weakly coupled Yang-Mills, we expect the free energy, prepotential interpreted as free energy, to be n squared. In the strong coupling region, hopefully if this observable is non-trivial enough, we expect n cubed. I mean, that's what we naively expect, although I didn't compute yet. So exact S-duality like this cannot balance this, right? Cannot make this mismatch happen, right? So in 6-dimensional generalization, we expect there to be a curious anomaly of S-duality generalized in this formula, if we consider the system of finitely two. And that kind of structure can be read off by carefully investigating this modular anomaly of the elliptic genus. And that will probably be the last explanation, the last subject that I'm going to explain to you today. So it's technical details. I just recorded for the completeness, but I'll just explain salient details in simple words. So if you don't want, please don't follow all the details. So a way of understanding the modular anomaly of this elliptic genus is the following. I explained to you that the elliptic genus is expressed in terms of a combination of Jacobi theta functions. So if you carefully investigate the Jacobi theta functions, it can be expressed in terms of what is called the Eisenstein series, if you expand in this elliptic parameter. And the modular property of the Eisenstein series is giving rise to this modular anomaly property. So what's called this Eisenstein series is generated by the three elements, E2, E4, and E6, and all the other elements, E4 and E6, are transforming very nicely in a modular way under the S-dual modular transformation. Only this one bad guy called E2 is transforming under the strange law. It has this affine shift part, which makes it quasi-modular form rather than exactly modular. So the E2 dependence appearing on this theta function is causing this modular anomaly of this elliptic genus. So if you make S-dual transformation for all Eisenstein series, there's a shift here, and this shift is causing this modular anomaly factor. Okay? So this coefficient is intimately related to the E2 dependence of the elliptic genus. So it can be phrased in the following way, which leads to what is called the modular anomaly equation. So you separate the tau dependence into the dependence through E2, the quasi-modular one, and the rest. And you take derivative of this elliptic genus as E2. And the right-hand side is the partition function itself, multiplied by the modular anomaly factor I explained to you in the few slides back. So this is a version of modular anomaly equation, which just rephrases what modular anomaly is. But now we are eventually interested in the grand partition function of alpha times T2. So you make a Laplace transformation, trading the string numbers by these Coulomb vectors. And then you replace all the string numbers by the derivative. It's kind of Fourier transformation. So you tend to find the following kind of partial differential equation. So the E2 derivative of the partition function or the wave function is given by the following quadratic operator and linear operator acting on the wave function. So we call this modular anomaly equation for the 2-0 Celsius strings. If you just stare at it, it formally looks very similar to the Schrödinger equation or heat equation. If you regard this E2 as time, and if you regard this tensor vector as space, with this peculiar first derivative shift. And you can massage this to make it into an exact heat equation by complete squaring this derivative, and you remain with a little bit of constant part. But the constant part appearing in the derivative can be understood as covariantization by background fields of time and space derivative. So the partition function appearing as a Lagrangian transformation can be dressed by the simple dressing factors depending linearly on the space and time coordinate, and it becomes what I call Z S-dual. And Z S-dual's S-duality transformation satisfies the formally exactly the heat equation. So we decompose the modular anomaly into two parts. The modular anomaly of this dressed wave function, which follows the heat equation, and the rest, which gives the extra anomaly of the S-duality transformation. And instantly you can observe this anomaly depending on the time-dependent part, or E2 dependent part, is precisely proportional to n cubed minus n. So there's a hope that we can strongly coupled free energies can be balanced by this modular anomaly factor. So it's just because this rho vector, which is a Weyl vector of the SUN, squares to the dual Coxeter number times the dimension of gauge group, which for SUN is n cubed minus n. Okay. So the modular transformation is divided into two parts. The first, I discussed the part governed by this heat wave equation for the dressed partition function. What we're really interested in is the free energy of that in certain limit. But the S-dualized, what I call Z S-dual, has a very simple S-duality transformation rule. So the S-dual transformation version can be expressed in this way. So it's nothing but a shift of this E2 Eisenstein parameter by a constant amount. So a shift by a wave function by a constant, which follows the wave equation given by this, can be a heat equation, can be expressed by a convolution by a heat kernel, which in this case is just a Gaussian vector. Okay? So considering our free energy limit, where we take a large volume limit, we make a saddle point approximation of this heat kernel convolution, and that gives exactly the 6-dimensional generalization of the Legendre transformation statement of S-duality. If you make a 4-dimensional reduction, it's precisely reducing to what we expect about Seiberg-Witten theory's electromagnetic duality. The more curious part is the anomalous part, right, which proportions n cubed minus n. Because if we had just this part, the strong coupling free energy and weak coupling free energy are so intimately related, so if it's proportional to n squared at small circle radius, it's also proportional to n squared at large circle radius. And that's not the right physics. But the S-dual anomaly part is making everything consistent. So the true free energy, including all the anomalous part, can be decomposed into F-S-dual, which follows this transformation rule of S-duality, plus some contribution from the tensor multiplier part, R is n, sorry, plus a term which is proportional to n cubed minus n. So this is the S-duality transformation structure. And we decompose the free energy this way, so that each term S-duality transformation can be traced explicitly. The S-duality transformation of this follows this generalized geometry transformation relation. The S-duality transformation of this tensor multiplier free energy and E2 can be explicitly done. It's so simple function. So using this anomalous S-duality transformation property of self-Dirichlet free energy, you can use the recoupling or low temperature or small radius result, which is governed by the perturbative Yang-Mills partition function, to understand the more challenging strong coupling, high temperature, and large radius regime. The result using that S-duality transformation is the following. There's an n-square part, which is just given by the fiber perturbative part, but the S-duality anomaly term gives the n-cube part, which allows us to have the desired n-cube scaling of the free energy when the circle radius becomes large. And so, in a sense, we have established using S-duality of the self-dual strings that it really encodes the n-cube degrees of freedom of the 6-dimensional 2-0 theory if we try to decompactify it. And in a sense, we have obtained the deconfined degrees of freedom of 6-dimensional theory, and there are lots of interesting physics, I think, related to some physics of black holes in ADS and so on, because the appearance of black hole is a deconfinement transition. But there are some physical works that I think can be done in the near future. So, well, 1.5 hours is very long. Neil wants I can give the rest of my time to. You had lots of interesting things at the end, right? So anyway, I have 2 more pages. I was asked by the organizers to finish by open questions and issues and so on. So I tried to finish by by explaining to you some ideas I thought to be interesting, but it's so wide and crude at this moment, so I didn't really find concretely where to put my ideas in concrete research settings. So I'll finish in the next slide by some wide comments. So if you think it's so crazy, please forgive me. So to summarize first, there has been lots of attempts towards microscopic formulations of this 6-dimensional component field theory. Many interesting ones: equational motions, Lagrangian. I'm following some of them quite eagerly. But as also Neil emphasized, there are lots of strong constraints that have to be met by any microscopic formulation. Okay, so some of them is S-duality, and another requirement is not just that it should host n-cube degrees of freedom, it should show the curious interpolation of the degrees of freedom as it changes the compactification radius. And there are more constraints that Neil has proposed, Neil has summarized to us, which I'm trying to digest at the moment. But anyway, I try to explain to you that many of the challenging aspects, naturally, are connected to the fields of six-dimensional self-pure strings, especially related to the anomaly structures on the S-duality. I haven't told you the details yet, but these are in turn intimately related to the Stooped anomaly structures that we heard of yesterday. And I try to make some of these connections quantitative, at least in some concrete setting. So I think there are much more interesting work to be done there, at least to develop concrete and interesting phenomena which should guide us better. And concerning these key themes that I explained to you, it's just throwing just crazy ideas, but first concerning S-duality, I try to emphasize along with me, that it's a highly non-trivial property of four-dimensional traditional gauge theory, but if we can realize the space-time Lorentz covariant description of six-dimensional quantum field theory, we expect it to be explained somewhat naturally. And that's, in my mind, one of the challenging aspects. Okay? So I'm always thinking of whether I can have an easier description, although it might look uglier. So there could be many non-covariant descriptions, non-manifestly Lorentz covariant descriptions. And many descriptions Neil emphasized to us are not manifestly covariant. Let's say like deconstruction description, large radius, limit of DSEQ maybe. But you know, it's intimately connected to treating, I think, electric and magnetic fields on equal footing. And I think more senior colleagues of mine should remember this work better, but there is an attempt by, I think, from Zwanzigo or somebody else, trying to treat these electric and magnetic fields in 4 dimensions and on equal footing. And incidentally, what he has to sacrifice is a manifest Lorentz invariance. So, along with these observations, I thought there would be more room for microscopic construction if you really try to accept perhaps ugly, non-manifest Lorentz invariant theory. But if this is allowing us exact quantum computation, to my eyes, that's good. So this might be another way that I'm quite interested in, and open our eyes to non-manifestly Lorentz covariant description, which might do lots of good quantum business. And also concerning self-duality of the 6-dimensional tensors. You know, there are many works on constructing the self-dual tensors equation of motion. If you want to write down the action of it, it's a bit difficult. I mean, self-dual middle forms are, the action principles are not very friendly to the self-dual middle form. There are ways to go around it, let's say in the PST formalism, which introduces more auxiliary fields to allow us to write down covariant Lagrangian for the self-dual middle form theories. But it's generally quite tricky, like the chiral bosons in 2D, self-dual free forms in 6D, and type 2D supergravity, which has self-dual 5 forms. But recently I learned that there appeared a way of writing covariant action of type 2D supergravity due to Ashok Sen, which doesn't really use this ad hoc manner of ignoring self-duality for a while, deriving the equation of motion, imposing it by hand, but it really is a type 2D supergravity action where you see the self-duality of the dynamical field just emerges. It seems to be a new mechanism, and the price for this is to have some extra degrees of freedom, which Ashok Sen shows exactly decouples with the other physical degrees of freedom. And he was inspired by the recent advances he achieved I understand, from type 2D string field theory, where the similar kind of extra degrees of freedom, decoupling with the rest of the setting, including gravity, everything happens. So this type 2D supergravity action seems to be a reflection of that, and it's sort of guaranteed to work at quantum level. So whenever you find the equation of motion, you're convinced of it, it might be valuable to think about this formulation to write down the quantum action, supposing that it survives all the other constraints. So these are 2 last ideas that I'd like to throw in, and I'll finish here. Thank you.
Thank you. So in 4D Yang-Mills and S-duality, you know that you go to the Langlands dual when you do S-duality. from SUN, I would then go to SUN1Z. So how do I see that from the 6-dimensional perspective when I just do S-duality in terms of changing cycles?
Probably the most natural thing to work with probably is UN, including this.
UN is...
Yeah. Including the central mass. Yeah.
Well, we should have an SUN.
Yeah,
This is linked with the conformal block of the CP.
Yeah, but then I want to see it.
Why do you think it's less UN theory?
You don't think there is an SUN theory?
I think there isn't.
Alright, let's do the D series. That's still not Langman subfield, but the D series.
Lang, that's up to right?
So
ADE is up to.
Self-dual on the Lie algebra,
Yeah.
but globally maybe not.
maybe it's always that's one of the reasons why it's
Yeah,
that's
my understanding.
Yeah, I'm always
Yeah,
confused with global
yeah,
structures.
I think one way to understand this is, from the 4D to D duality,
Yeah.
you have this relationship to affine algebras. And so at the algebraic level, Lie algebraic level, the S-duality for ADE is self-dual.
Yeah.
So, but at the global level, like you mentioned, SUN goes to SUN mod CN. So that's a bit not so clear.
Further questions?
So in the action for the n equals 1, 0 theory, you said optionally we can add Yang-Mills like terms. With a constant.
Depending on models, you have to add it.
Okay. But there was a three-factor constant C squared.
Oh yeah.
Does that have a meaning?
That depends on the model. It depends on depends on the gauge group choice. It depends on the number of hypermodular matters. The C has to be dependent on the size of the gauge group or the number of flavor fields and so on. So once you're given the models, there are concrete expressions given for C. I just want it to be generic. So yeah. Like functions of NC, NF, and so on. Yeah.
So.
Yeah, a really vague question. I think I've heard people say that the 2,0 theory is a limit of the 60 self-dual string theory.
60. Oh yeah. I think I understand what you mean. So there are hierarchies of theories. Today I try to explain directly obtaining 620 superconformal field theory from big string theory, but you can do it in some steps. So obtaining field theory from string theory is a kind of low energy limits and many degrees of freedom decouple. But you can take a more elaborate decoupling limit without taking low energy. So if you keep suitably string tension finite, but take some suitable limits of coupling 0 or something, you can have some string theory localized on the 6th dimension decoupled from gravity. So we call this little string theory. Okay? So probably the self-theory string theory you mentioned is this little string theory, which is a non-local theory, but it doesn't have gravity. If you take a further low energy limit of these string theories, you get this field theory that I mentioned. Yes, that's the relation.
But self-dual strings are not the strings of the little string theory.
The string I mentioned. The string, of course, this is part of the string theory spectrum, but there are more strings appearing. Yeah. And these new strings are tensionful even at the symmetric phase. Yeah.
So essentially, the massive sector for this little string contains the B mu V, like in regular string theory, and that is supposed to be sourced by a solitonic object, okay, and that sources the B mu V that you're looking at. So those things that source the B mu V, that's the self-dual strings, which are the M-branes ending between the M5. Those strings he's talking about. Yeah, M-branes, M2 branes ending on the M5, but with the other direction wrapping the 11th circle. That's outside of the M5. Yeah, so there are two types of strings. Yeah.
I'm talking about open M2 branes suspended between M5, but in little string theory there's a circle, so this open M5 M2s can combine to be a closed M2 branes, and they give rise to with little strings.
So you computed the elliptic genus for self-dual strings, and there was this modular anomaly, right? So are you saying that SL2Z is not a exact symmetry of the 2,0 theory? What do you mean?
Yeah. I mean, there's some part of the modular anomaly, some part of the modular anomaly factor I explained to you, that translates into the standard S-duality transformation of the four-dimensional prepotential. You know, prepotential is not left invariant, but if you change it to magnetic description, it undergoes Legendre transformation. That rule is derived by part of the modular anomaly. But there's the rest of the modular anomaly factor, proportional to n cubed minus n, and that survives only for finite torus. If you take a small torus limit, that term just vanishes to zero. But on finite torus, there should be extra modular anomaly factor on top of this Legendre transformation formula. That's what I established. And that plays crucial role for balancing this 5D and 6D n squared n cubed mismatch of the free energy. Yeah.
Just one small comment perhaps on this. An action for a 6D self-dual theory. I mean, so you can look already just in 2D Carroll bosons, and then we know that an action is not enough to specify a partition function of a Carroll boson. Essentially because we sort of, the quickest way to see it is that you can fermionize, because it's self-dual, and then it goes into a Val fermion, and then you can have anti-periodic boundary conditions as well, if you've got a compact cycle. So that then there's an ambiguity of the partition function, which is the fact you can have two theta functions that are specified. Now the action doesn't contain that information. So in some sense, even if you have an action, you don't completely specify the partition function of the Carroll boson.
Yeah, good. But still I want to have an action. If possible. Yeah, I appreciate that.